Hello there, and welcome to Earth's history, where the present becomes a doorway to the deep past, and science unfolds like a story told in whispers. Tonight, we're following something so familiar that we rarely stop to wonder about it. Something you've touched today, something you've tasted, something that covers most of our planet and flows through every living cell. Water. Simple, clear, essential. But where did it come from? Before there were oceans, before there were clouds, or rain, or morning dew, there was a planet made of fire and stone. A world so hot that water, if it existed at all, could not stay. It would have turned to steam in an instant, vanishing into a sky that barely existed. And yet, somehow, against all the odds and over hundreds of millions of years, water found its way here. It traveled across vast distances, carried by ice and stone, delivered by forces we're only beginning to understand. And once it arrived, it transformed everything. This is the story of that journey. Not just how water came to Earth, but what it took to get here, what it changed when it arrived, and why every drop you've ever known is older than anything you can imagine. Older than mountain, older than life, older even than the ground beneath your feet. Wherever you are right now, listening to this, I hope you're comfortable. Maybe you're curled up in bed, or sitting quietly in a dim room, or watching the evening settle outside your window. If this gentle unfolding of an ancient mystery brings you even a moment of peace, I'd be grateful if you'd like the video, maybe subscribe, or share it with someone else who finds comfort in the slow turning of deep time. It helps this quiet corner reach others who need a place to rest at the end of the day. So take a breath, let your thoughts settle like dust after a long wind, and let's begin. Because long before you or I existed, long before anything we recognize as familiar, water was already on its way, traveling through darkness and cold, through the vast empty spaces between worlds, carried on the backs of wanderers made of ice and stone. And when it finally arrived here, it made this planet home. The story begins not with water, but with its absence. Picture Earth in its earliest day, just after it had gathered itself from the swirling disk of dust and gas that surrounded the young sun. This was not the blue planet we know. There was no ocean to catch the light, no clouds drifting across the sky, no rain to fall on thirsty ground. Instead, there was only heat, unimaginable, all-consuming heat. The surface of the newborn Earth was molten. Rivers of liquid rock flowed across its face, glowing orange and red in the darkness of space. Where continents would one day rise, there was only magma, shifting and churning in slow, heavy current. The sky, if you could call it that, was thick with vapor, rock dust, and the glow of impact after impact as the last pieces of planetary debris crashed into the growing world. This was a planet still being born, still gathering itself, still too hot to hold anything as delicate as water. And even if water had been there, it would not have stayed. The temperature was far too high. Water, when heated beyond its boiling point, becomes steam. And steam, without an atmosphere to contain it, simply drifts away into space. So even though the ingredients for water, hydrogen, and oxygen were present in the materials that formed Earth, the water itself had no place to settle. It was driven off, lost, scattered into the void. This was Earth's first great paradox. It was born in fire, shaped by violence, and yet it would need to become a world of water in order to become a world of life. How does a planet of fire become a planet of ocean? The answer is not simple, and it's not quick. It took hundreds of millions of years, and it required help from beyond. But before we follow that help inward, before we trace the journey of water across the solar system, we need to understand what water is and where it comes from in the first place. Because water is not rare in the universe. In fact, it is everywhere. It's one of the most common molecules in existence, and that in itself is a kind of mirror. Water is made of two elements, hydrogen and oxygen. Hydrogen is the simplest and most abundant element in the universe, forged in the moments after the Big Bang. Oxygen, on the other hand, is heavier. It's created in the hearts of stars, built up through fusion as stars burn their fuel, and eventually scattered into space when those stars die. Every atom of oxygen in your body, in the air you breathe, in the water you drink, was once inside a star. It was born in fire, ejected in a supernova, and spread across the cosmos in vast clouds of gas and dust. When hydrogen and oxygen meet in the cold depths of space, they bond. Two hydrogen atoms attach to one oxygen atom, forming H2O. This happens in the molecular clouds that drift between stars, in the disks of gas and dust that surround newborn sun, and on the surfaces of tiny grains of dust and ice floating through the void. Water ice coats asteroid. It fills the hearts of comets. It hides in the minerals of meteorite. The universe is full of water, waiting. Our solar system too was born from such a cloud. About 4.6 billion years ago, a region of a much larger molecular cloud began to collapse under its own gravity. Perhaps it was triggered by the shockwave of a nearby supernova. Perhaps it was simply time. Whatever the cause, the cloud began to spin and contract, forming a disk with the sun igniting at its center. And in that disk, water was everywhere. But not everywhere was cold enough for water to stay frozen. Close to the sun, where Earth would eventually form, the heat was intense. Here, in what astronomers call the inner solar system, water evaporated. It became gas, drifting outward on the solar wind, unable to condense. This region, the zone where the rocky planet, Mercury, Venus, Earth, and Mars would coalesce, was dry. The materials that gathered here were mostly metal and rock, silicates and iron, substances that could withstand the heat. Farther out, beyond a boundary called the frost line or snow line, it was a different story. Out there, beyond the orbit of what would become Mars, temperatures were low enough for water to freeze. Ice could exist. And where ice existed, it could gather. This is where the giant planets formed: Jupiter, Saturn, Uranus, Neptune, worlds massive enough to capture not only rock and metal, but also vast amounts of ice and gas. And beyond them, in the cold outer reaches of the solar system, ice ruled. Comets formed in the Kuiper Belt and the distant Oort cloud, vast reservoirs of frozen water wrapped in stone, waiting in the dark. So when Earth formed, it was in the wrong place. It was too close to the sun, too hot, too dry, and yet we know that it did not stay that way. Somehow, water crossed the frost line. Somehow, it found its way inward. Somehow, it reached Earth. And the question that has occupied scientists for decades is simple but profound. How? There are three main ideas, three pathways by which water might have arrived. The first is comets, the second is asteroids, and the third is that the water was here all along, trapped inside Earth's interior, waiting to be released. Each of these ideas has evidence. Each has challenges. And the truth, as with so many things in science, is likely a combination of all three. Let's begin with comets. They are, in many ways, the most romantic answer. Imagine them as messengers from the edge of the solar system, ancient wanderers made of ice and dust, their tails streaming behind them as they fall toward the sun. Comets are often called dirty snowballs, though that phrase hardly does them justice. They are leftover fragments from the formation of the solar system, preserved in the deep freeze of the outer reaches, barely changed since the sun first ignited. Their ice is not just water. It's a mix of water, carbon dioxide, methane, ammonia, all the volatiles that were once common in the early solar nebula. When a comet's orbit brings it close to the sun, the ice begins to sublimate, turning directly from solid to gas. This creates the comet's glowing coma and its long sweeping tail. For centuries, humans have watched comets with wonder and sometimes fear, but now we know that they are not omens. They are time capsules, and more than that, they may be delivery vehicles. In the early days of the solar system, the orbits of the planets were still shifting. Jupiter, massive and powerful, acted like a gravitational shepherd, flinging objects inward and outward with its immense pull. Some of those objects were comets. Nudged out of their distant orbits, they began long, slow falls toward the inner solar system, and some of them struck Earth. During a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago, the inner planets were pelted with impacts. Asteroids and comets crashed into their surfaces, leaving craters and scars that, on Earth, have long since been erased by erosion and plate tectonics, but which are still visible on the Moon and Mars. This bombardment was intense. And if many of those impactors were comets, they would have brought water, lots of it. Each impact would have delivered ice that vaporized on contact, filling the air with steam, which would eventually cool and fall as rain. For a long time, this was the leading theory. Comets brought the ocean. It was a beautiful idea, poetic even. Water delivered from the frozen edge of the solar system, a gift from the void. But then we began to study comets more closely. In recent decades, missions like Rosetta, which followed Comet 67P for months, and instruments that analyzed the light and gas from other passing comets, revealed something unexpected. The water in many comets doesn't quite match the water on Earth. Here's why that matters. Not all water is the same. Most water molecules are made of ordinary hydrogen, but a small fraction contain deuterium, a heavier isotope of hydrogen with an extra neutron. The ratio of deuterium to hydrogen, called the DH ratio, is like a fingerprint. Different regions of the solar system have different DH ratios, depending on the temperature and conditions when the water formed. Earth's oceans have a specific DH ratio, and when scientists measured the DH ratio of water vapor from comets, especially those from the distant Oort cloud, they found that it was often much higher, sometimes twice as high as Earth. That suggests that water from those comets is not the primary source of Earth's ocean. It might have contributed, but it couldn't have delivered all of it. However, not all comets are the same. Comets from the Kuiper Belt, a region closer than the Oort cloud, seem to have DH ratios much closer to Earth's. One comet in particular, 103P Hartley 2, had a nearly perfect match. So comets may still have played a role, but if they did, it was likely the closer one, and perhaps only part of the story. This is where asteroids enter the picture, and with them, the story becomes both simpler and stranger. Asteroids are often thought of as dry, lifeless rocks, chunks of metal and stone left over from the failed formation of a planet between Mars and Jupiter. But some asteroids, particularly a type called carbonaceous chondrites, are not dry at all. They contain water, not as ice on the surface, but locked inside their minerals, bound chemically into the structure of clays and other hydrated compounds. Some of these asteroids are up to 10% water by weight. That might not sound like much, but when you consider the billions upon billions of asteroids that existed in the early solar system, it adds up. And here's the crucial part. When scientists have analyzed meteorites that came from carbonaceous chondrite, meteorites that have fallen to Earth and been carefully studied, they've found something remarkable. The DH ratio of the water in those meteorites matches the DH ratio of Earth's oceans almost perfectly. It's a closer match than most comets. This suggests that asteroids, not comets, may have been the primary source of Earth's water. But how did water from asteroids get here? The same way comets did. Impact. In the early solar system, as the planets jostled for position and Jupiter's gravity stirred the asteroid belt, countless asteroids were flung inward. They bombarded the inner planet. And when they struck Earth, the heat of the impact released the water trapped in their minerals. It vaporized, mixed with the atmosphere, and eventually condensed. Over millions of years, impact after impact, the water accumulated. Picture it, a young Earth, its surface still cooling, its sky clearing, and from the darkness above, a streak of light, an asteroid, perhaps a kilometer across, falling faster than sound. It strikes, the ground vaporizes, a plume of rock and steam rises into the sky. The impact crater glows red, then cools, and the steam, no longer hot enough to escape into space, begins to fall. Rain, the first rain, and then more impact and more rain. A slow, steady delivery over tens of millions of years. But there's a third possibility, one that doesn't require any delivery from space at all. What if the water was already here, trapped inside Earth from the very beginning? When Earth formed, it gathered material from the solar nebula. Most of that material was rock and metal, yes, but even in the hot inner solar system, some minerals can hold onto water, not as liquid or ice, but chemically bound in their crystal structure. These hydrated minerals would have been incorporated into Earth as it grew, and as the planet heated up, as its interior melted and differentiated into layers, that water would have been released. It would have risen through the mantle, carried by volcanic eruption, and expelled into the atmosphere as steam. This process is called outgassing, and we know it happened because it's still happening today. Every time a volcano erupts, it releases gases: water vapor, carbon dioxide, sulfur dioxide. Much of that water comes from deep within the earth, from minerals in the mantle that break down under heat and pressure. If this process has been going on for billions of years, and there's every reason to think it has, then some, perhaps even most, of Earth's water could be homegrown. The evidence for this comes from studying the deep Earth. Samples of mantle rock brought to the surface by volcanic activity show that the mantle contains water. Not vast underground ocean, but water locked in minerals like ringwoodite, which can hold water in its structure under high pressure. In fact, scientists estimate that there may be as much water in the mantle as there is in all the world's oceans combined. It's hidden, trapped, slowly cycling through the planet's interior over geological time. So which is it? Did water come from comets, from asteroids, or from within? The answer, almost certainly, is all three. Earth's water is not from a single source. It's a blend, a mix of cosmic ice delivered by impacts and volcanic steam released from the interior. Some of it fell from the sky, some of it rose from below, and together they filled the oceans. But knowing where water came from is only half the story. The other half, just as important, is when it arrived and how it stayed. Let's step back to that early Earth again. The surface is cooling, but it's still hot. The atmosphere is thick with carbon dioxide and steam. The sky is perpetually cloudy, and somewhere, in a low-lying basin where the crust has begun to solidify, a puddle formed. Just a puddle. The first liquid water on the surface of Earth. It doesn't last long. The heat evaporates it, but it returns again and again. Puddle, evaporation, condensation, rain. The first stirrings of the water cycle. As the planet continues to cool, those puddles last longer. They spread, they connect, streams form, then rivers, then lakes, and eventually, perhaps as early as 4.4 billion years ago, the first ocean. We know this from zircon, tiny crystals, often no larger than a grain of sand, that form in molten rock and are nearly indestructible. Some of the oldest zircons on Earth, found in the Jack Hills of Western Australia, are over 4.4 billion years old. And when scientists analyze the chemistry of these ancient crystals, they find something astonishing. The oxygen isotopes in the zircons suggest that they formed in the presence of liquid water, not just steam, liquid water. Which means that just 160 million years after Earth formed, less than 200 million years after the solar system itself began, there were already oceans. This is shockingly fast. It means that Earth did not spend billions of years as a dry, lifeless rock. It became a water world almost immediately, geologically speaking. And once the water was here, it stayed. But why did it stay on Earth and not on Venus or Mars? Why did Earth become the blue planet? The answer has to do with size, distance, and luck. Venus is almost the same size as Earth, but it's closer to the sun. The extra heat meant that any water on its surface evaporated. Water vapor rose into the upper atmosphere, where ultraviolet light from the sun broke it apart into hydrogen and oxygen. The hydrogen, being light, escaped into space. The oxygen reacted with rock. Over time, Venus lost its water. Today, it's a scorched, dry world with crushing atmospheric pressure and surface temperatures hot enough to melt lead. Mars, on the other hand, is smaller than Earth, and that was its downfall. A smaller planet cools fast. Its interior solidified more quickly, shutting down volcanic activity and, crucially, its magnetic field. Without a magnetic field to protect it, the solar wind, a stream of charged particles from the sun, began stripping away Mars's atmosphere, and with the atmosphere went the water. Some of it is still there, frozen at the poles or hidden as ice beneath the surface. But Mars lost most of its water to space. Earth, by contrast, was just right. It was far enough from the sun that water could condense. It was large enough to hold onto its atmosphere and maintain a magnetic field. And it had active plate tectonic, a process that recycled water between the surface and the interior, keeping the planet geologically alive. Earth held onto its water, and that water changed everything. The first oceans were not like the oceans we know. They were hot, perhaps as warm as 70 or 80 degrees Celsius in some places, far warmer than a comfortable bath. They were acidic too, laced with dissolved carbon dioxide from the thick atmosphere, and they were rich in mineral, iron, silica, salt, all leached from the newly formed rock. The water was likely greenish or brownish, clouded with sediments and dissolved metals. There were no continents yet, or if there were, they were small volcanic islands poking above the waves. Most of the planet was covered by a single vast ocean. But even in this harsh, alien sea, chemistry was happening. Water is an extraordinary solvent. It dissolves minerals. It carries ions. It allows molecules to move and interact in ways that would be impossible in ice or gas. And in the warm, mineral-rich waters of the early ocean, complex chemistry began. Amino acids formed, nucleotides assembled, lipids, simple fatty molecules spontaneously organized into bubbles, primitive cell membrane. Water, it turned out, was not just essential for life. It was the medium in which life could begin. We don't know exactly when or where life started, but we know it happened early. The oldest evidence of life, chemical signatures in rock from Greenland and Western Australia, date back 3.8 to 3.5 billion years ago. That's less than a billion years after the ocean's form. In geological terms, life appeared almost as soon as it possibly could, and that suggests something profound. Given water, given time, given the right chemistry, life is not a fluke. It's a possibility waiting to happen. But water didn't just enable life. It shaped the planet in other ways too. It sculpted the land. Rain fell on volcanic rock, dissolving minerals, carrying them to the sea. This process, called weathering, created the first sediment. Over time, these sediments accumulated on the ocean floor, forming the earliest sedimentary rock. Some of these rocks still exist today, preserved in places like Greenland and Canada, silent witnesses to a time when the world was young. Water also regulated the climate. The early atmosphere was thick with carbon dioxide, a greenhouse gas that kept the planet warm, even though the young sun was dimmer than it is today. But water, through the process of weathering, slowly removed carbon dioxide from the air. Rain dissolved CO2, forming a weak acid that reacted with rock, locking the carbon away in minerals like limestone. This process, which continues to this day, kept Earth's climate stable. Without it, Earth might have become too hot or too cold to sustain life, and water cycled. Even in those early days, the water cycle was already at work. Evaporation, condensation, precipitation. Water moved from the ocean to the sky and back again. It carved rivers, filled lakes, sank into the ground, and emerged as spring. It was never still. It was always in motion. And that motion connected every part of the planet. The ocean, the land, the atmosphere, the deep interior. Water tied it all together. As the planet continued to evolve, water played a role in almost every major transformation. When the first continents began to rise, pushed up by tectonic forces, water eroded them, carving valleys and canyons. When life spread from the oceans onto land, it was water that made that transition possible. Plants needed water to survive. Animals followed the water. Entire ecosystems formed along rivers and lakes. Even the great mass extinction, the catastrophes that wiped out countless species, were often linked to changes in the ocean, shifts in temperature, in chemistry, in circulation. Water giveth and water taketh away. But through it all, the water itself remained. The same water that fell as rain on the early Earth is still here. It has cycled through oceans and clouds, through rivers and ice, through the bodies of countless living things. It has been locked in glaciers for millions of years, then released. It has sunk into the mantle, been spewed out by volcanoes, and fallen as rain again. Water is ancient. The water in your body right now, the water you drank this morning, is billions of years old. It's older than the dinosaur, older than the mountain, older than complex life itself, and it's still arriving. Even today, water continues to reach Earth from space, not in great floods, but in tiny amounts. Micrometeorite, grains of dust no larger than a speck of sand, drift down from space every day. Many of them contain water ice. It's a slow delivery, nothing like the bombardment of the early solar system, but it's a reminder that Earth is still part of a larger system. We're still connected to the cosmos. There's something humbling in that. We think of Earth as isolated, a self-contained world spinning in the void, but it's not. It never was. We're part of the solar system. We're made of the same materials as asteroids and comets. The water we drink came from the same cloud that formed the sun. The oxygen we breathe was made in stars. We're not separate from the universe. We're woven into it, and water is the thread that ties us to that history. Every time you wash your hand, every time you watch rain fall, every time you stand by the ocean and listen to the wave, you're touching something that traveled across space to get here, something that survived impacts and heat and the slow, patient cooling of a planet, something that, against all odds, found a home. So let's follow that journey one more time, but slower now, with more care. Let's trace the path of a single water molecule, from its origins to the present. It's a story worth savoring. Our molecule begins in a molecular cloud, not the one that formed our solar system, but an earlier one, a vast, cold region of space where gas and dust drift in darkness. Here, far from any star, the temperature is barely above absolute zero. Hydrogen atoms, the most common element in the universe, drift slowly through the void. Occasionally, they encounter a grain of dust, a tiny particle of silicate or carbon, and they stick to it. Over time, more hydrogen accumulates. And when oxygen atoms, forged in the death of an earlier star and scattered into space, also land on the grain, a reaction happens. Two hydrogen atoms and one oxygen atom bond, forming water ice, a single molecule frozen onto a speck of dust. This molecule drifts in the cloud for millions of years. The cloud is vast, light years across. Nothing seems to happen, but eventually, the cloud begins to collapse. Perhaps a shock wave from a nearby supernova disturbs it. Perhaps it simply becomes dense enough that its own gravity takes over. Whatever the cause, the cloud begins to fall inward, slowly at first, then faster. It spins as it collapses, forming a disk, and at the center, where the density and temperature are highest, a star begins to form. Our sun, the water molecule, still clinging to its grain of dust, is caught in this disk. It orbits the young sun, spiraling inward with countless other grains. The closer it gets to the sun, the warmer it becomes. In the innermost regions, close to where Earth will form, the temperature is too high. Water ice sublimates, turning to vapor. But our molecule is farther out, beyond the frost line. Here, it stays frozen. Over time, the grains of dust begin to stick together. Electrostatic forces and gentle collisions bind them into larger clumps. These clumps collide with other clumps, growing larger still. This process, called accretion, is slow but relentless. Dust becomes pebbles. Pebbles become boulders. Boulders become planetesimals, objects kilometers across. And some of these planetesimals, rich in water ice, become the cores of comets or asteroids. Our water molecule is now part of a small asteroid, drifting in the region beyond Mars. It's been frozen for millions of years, locked in the dark interior of a rock. The asteroid orbits peacefully for a time, but the early solar system is chaotic. Gravitational interactions with the growing planets, especially Jupiter, perturb the orbits of asteroids. Some are flung outward into the distant reaches of the solar system. Others are flung inward. Our asteroid is one of the unlucky ones. Its orbit shifts, bringing it closer to the sun. It crosses the orbit of Mars, then approaches Earth, and one day, about 4 billion years ago, it falls. The asteroid enters Earth's atmosphere at tremendous speed. The air in front of it compresses and heats, glowing white hot. The asteroid itself begins to glow, and then, in a fraction of a second, it strikes the surface. The impact is cataclysmic. The asteroid, perhaps a few hundred meters across, releases energy equivalent to millions of tons of TNT. The ground vaporizes. A shockwave radiates outward, flattening everything nearby. A plume of molten rock and vapor rises into the sky, glowing orange and red. And in that plume, our water molecule, locked in the asteroid's minerals, is released. The heat breaks the chemical bond. The water turns to steam. For a moment, it seems as though the molecule will be lost. The temperature is high enough that it could escape into space, but the steam rises into the atmosphere and begins to cool. Earth's gravity holds it. The atmosphere, thick with volcanic gases and steam from countless other impacts, traps it. And as the hours pass and the days, The steam condenses. It forms droplets, and those droplets fall. Rain. Not gentle rain, but a torrent. The sky is dark with clouds. Lightning flashes. Thunder rolls across the still barren land. And the rain falls, warm at first, then cooler, pooling in the low places, running across the rock, gathering into stream. Our water molecule, now part of a raindrop, falls onto the surface of the early Earth. It hits the ground and flows, joining other droplets, moving downhill, pulled by gravity. It reaches a basin, a low point in the newly formed crust, and there it settles. It's part of the ocean now, but its journey is far from over. The ocean is warm and restless. Currents carry the molecule across vast distances. It circulates, mixing with other water, absorbing minerals from the rocks below. It evaporates, rising into the atmosphere as vapor once again. It travels with the wind, drifts over land, condenses into a cloud, and falls as rain onto a volcanic island. It seeps into the ground, percolates through cracks in the rock, and emerges from a hot spring, steaming in the cool air. It flows back to the sea. This cycle repeats for billions of years. The molecule is never still. It evaporates and condenses, freezes and melts, flows and seeps. It's part of glaciers that cover entire continents during ice ages. It's part of rivers that carve canyons. It's part of the seas that flood vast plains. It's absorbed by the first microbes, simple cells that use it to survive. It's part of the cytoplasm, the medium in which life's chemistry unfolds. It's released when those cells die, returning to the environment. It's part of a raindrop that falls on a carboniferous forest 300 million years ago. It's absorbed by a towering tree fern, pulled up through its roots, used in photosynthesis, then released through its leaves as vapor. It rises into the sky, part of a cloud that drifts across the supercontinent of Pangaea. It falls again, this time into a river. It flows across the land, past herds of early reptiles drinking at the water's edge. It reaches the ocean once more. It's part of the sea that covers much of North America during the Cretaceous, a warm, shallow sea teeming with ammonites and mosasaurs. It evaporates under a hot sun, forms a cloud, and falls as rain on the floodplains where dinosaurs graze. It soaks into the soil, is drawn up by the roots of flowering plants, the first flowers, and becomes part of their sap. When the plant dies, the water seeps back into the ground. It's part of a glacier during the last ice age, frozen for tens of thousands of years. As the ice sheet spreads across the northern continent, it moves slowly, grinding rock into dust, carving valleys. And when the climate warms, it melts. It flows into a stream, then a river, and finally into the ocean. It's part of the Atlantic now, circulating in the Gulf Stream, carrying warmth northward, and eventually it's part of a cloud that forms over the land where you live. It falls as rain. It lands on your roof, flows into a river, is treated at a water plant, and comes out of your tap. You pour it into a glass, you drink it, and for a brief moment, that ancient molecule, billions of years old, is part of you. It's in your blood, carrying oxygen to your cell. It's in your cell, the medium in which proteins fold and enzymes catalyze reaction. It's part of your thought. Because your brain is mostly water. Every neuron, every synapse depends on it. And then you exhale, or you sweat, or you go to the bathroom, and the molecule leaves your body. It returns to the environment. It evaporates, or it flows into the sewer, is treated, and released into a river. And the cycle continues. This is the story of water. Not a simple story, but a layered one. A story of cosmic origins and planetary transformation. A story of ice and fire, of impacts and eruption, of cycles that have repeated for billions of years. Water came from the stars. It traveled through space. It survived the violence of Earth's formation. It filled the ocean. It carved the land. It enabled life. And it's still here, still moving, still cycling, still essential. There's a paradox in all of this. Water is so common, so familiar, that we take it for granted. We turn on a tap and expect it to flow. We see rain and think nothing of it. We stand by the ocean and barely consider what we're looking. And yet, when you understand where water came from, when you trace its journey across space and time, it becomes anything but ordinary. It becomes miraculous. Think about it. The water in your body is the same water that cooled the early Earth, the same water that filled the first ocean, the same water that nurtured the first life. It's cycled through countless organisms, from bacteria to dinosaurs to you. It's been vapor and ice and liquid over and over again. It's crossed continents and oceans. It's fallen as snow on mountains that no longer exist. It's flowed through rivers that have dried up and disappeared. And yet, it's still here, still moving, still essential. And it's not just Earth's water that has this history. Water is everywhere in the universe. It's in the atmospheres of gas giants. It's in the rings of Saturn. It's frozen on the moons of Jupiter and Saturn. Enceladus, one of Saturn's moons, has geysers that shoot water vapor into space. Europa, a moon of Jupiter, has a subsurface ocean larger than all of Earth's oceans combined, hidden beneath a thick shell of ice. Mars has ice at its poles and possibly liquid water beneath its surface. Even the moon has water, frozen in permanently shadowed craters at the poles. Beyond our solar system, water has been detected in the atmospheres of exoplanets, planets orbiting other stars. Some of these planets are in the habitable zone, the region where temperatures are right for liquid water to exist on the surface. And wherever there's liquid water, there's the possibility of life. Not certainty, but possibility. Because water is the universal solvent, the medium in which chemistry flourishes, and life, as far as we know, requires chemistry. This raises a profound question. If water is common in the universe, and if life requires water, does that mean life is common too? We don't know. We've only ever found life on one planet. But the fact that life on Earth appeared so quickly after the oceans formed suggests that it's not as improbable as we once thought. Given the right condition, life might be, if not inevitable, at least likely. And if that's true, if there are other worlds out there with water and life, then the story of how water came to Earth is not just our story. It's a universal story. It's a pattern that has played out on countless worlds across the cosmos. Water forms in molecular clouds. It's incorporated into planets. It cycles through their surfaces and atmospheres, and on some of those planets, it gives rise to life. Each world has its own version of the story, but the broad strokes are the same. But even if we're alone, even if Earth is the only planet in the universe with life, the story of water is still worth telling, because it reminds us of what we are. We're not separate from the universe. We're part of it. The atoms in our bodies were made in stars. The water in our cells traveled through space. We're made of the cosmos. And when we look up at the night sky, we're not looking at something foreign or distant. We're looking at home. We're looking at the place we came from. There's a kind of poetry in that realization, a kind of comfort, because it means that no matter how isolated we might feel, no matter how small or insignificant, we're connected to something vast and ancient. Every breath you take contains atoms that have cycled through the atmosphere for billions of years. Every drink of water connects you to the earliest ocean, to comets and asteroids, to the molecular clouds between the stars. You are, in the most literal sense, made of stardust and ancient rain. And yet, for all its cosmic origins, water is also deeply personal. It's the most intimate substance we know. It's inside you right now, making up about 60% of your body weight. It's in every cell, every tissue, every organ. Your blood is mostly water. Your brain floats in water. Your eyes are filled with water. Even your bones, which seem so solid, are about 30% water. Without it, you would cease to function in a matter of days. Water is not just something you need, it's something you are. This intimacy extends to our relationship with the planet. We don't just live on Earth. We're part of Earth's water cycle. When you drink water, you're borrowing it from the planet. When you release it, you're returning it. The boundary between you and the environment is not as clear as it seems. You're not a separate thing moving through the world. You're a temporary eddy in the flow of matter and energy that has been moving through this planet for billions of years. And the water itself remembers, in a sense. Not in the way we remember, with thoughts and feeling, but in its patterns, in its chemistry. The isotopes in water molecules carry information about where they've been, what temperatures they've experienced, what rocks they've interacted with. Scientists can read this information, tracing water back through time, reconstructing ancient climates and environments. Ice cores from Antarctica and Greenland contain water that fell as snow hundreds of thousands of years ago, and trapped in that ice are tiny bubbles of ancient air. By studying these cores, scientists can measure the temperature and atmospheric composition of the past, year by year, going back nearly 1,000,000 years. Even the salinity of the ocean carries memory. The ocean is salty because water, as it flows over rocks and soil, dissolves minerals and carries them to the sea. Over billions of years, those minerals have accumulated. The salt in seawater is ancient, a residue of eons of weathering and erosion. When you taste the ocean, you're tasting the dissolved remnants of mountains that no longer exist, of rocks worn away by rain and river, of volcanic gas released into ancient sea. This long memory of water also appears in caves. Stalactites and stalagmites form as water, carrying dissolved mineral, drips slowly from cave ceiling. Each drip deposits a thin layer of calcite. Over thousands of years, these layers build up, creating formations that can be meters tall. And within those layers, the chemistry of the water is preserved. Scientists can cut through a stalagmite and read it like a tree ring, measuring the ratios of different isotopes to reconstruct how much rain fell in each year, how warm or cold it was, even what kinds of plants were growing on the surface above the cave. Water writes the history of the planet in stone. But water is not just a passive recorder. It's an active force. It shapes the land in profound way. Erosion, the wearing away of rock by water, wind, and ice, is one of the most powerful geological processes on Earth. Rivers carve canyons. Rain dissolves limestone, creating caves. Glaciers grind mountains into valleys. Even the slow creep of groundwater, percolating through rock, dissolves minerals and creates underground rivers and chambers. The Grand Canyon, one of Earth's most spectacular landscapes, was carved by the Colorado River over millions of years. Layer by layer, the river cut down through rock, exposing nearly 2 billion years of geological history. Standing at the rim and looking down, you're seeing time made visible. And the agent of that visibility is water, patient, relentless, unstoppable. Water also builds. When it evaporates from the ocean, it leaves salt behind. In some places, where seawater is trapped in shallow basins and evaporates faster than it's replenished, thick layers of salt accumulate. These salt deposits, some of them thousands of meters thick, are the remnants of ancient seas that dried up millions of years ago. And when those deposits are buried and subjected to heat and pressure, they can flow like a viscous fluid, rising through overlying rock layers to form salt domes. These structures, besides being geologically fascinating, often trap oil and natural gas, making them economically important. Water transport. Rivers carry sediment from mountains to the sea. Over time, this sediment accumulates in deltas and on continental shelves, building up thick layers that can eventually become sedimentary rock. The Mississippi River, for example, carries about 500 million tons of sediment to the Gulf of Mexico every year. Over millions of years, this sediment has built the vast delta of Louisiana, a landscape of marshes and channels that is constantly being reshaped by the flow of water, and water regulate. The ocean is Earth's thermostat because water has a high heat capacity, meaning it takes a lot of energy to change its temperature. The ocean absorbs heat during the summer and releases it during the winter, moderating temperature swing. Ocean currents redistribute this heat around the planet. Warm water flows from the equator toward the poles, while cold water flows from the poles toward the equator. This circulation, driven by differences in temperature and salinity, is called thermohaline circulation, and it plays a crucial role in regulating Earth's climate. Without the ocean, Earth would be a planet of extreme. Temperatures would swing wildly between day and night, between summer and winter. The equator would be unbearably hot, the poles unbearably cold, but the ocean smooths out these extremes, making Earth a more habitable place. Water also moderates the atmosphere. Through evaporation and condensation, water moves heat from the surface into the atmosphere and redistributes it through weather systems. Hurricanes, for example, are essentially heat engines powered by the evaporation of warm seawater. They form over tropical ocean, where water temperatures are high, and they release enormous amounts of energy as the water vapor condenses back into liquid, forming clouds and rain. In this way, water helps transport heat from the tropics toward higher latitudes, balancing the planet's energy budget. And then, There's the water cycle itself, one of Earth's most fundamental processes. Water evaporates from the ocean, rises into the atmosphere, condenses into clouds, falls as rain or snow, flows across the land in rivers and streams, and returns to the ocean. This cycle has been running for billions of years, and it connects every part of the planet. The rain that falls on a mountain in the Himalayas eventually flows into a river, crosses the plains of India, and reaches the Indian Ocean. From there, it evaporates, travels with the wind, and might fall as rain in Africa or South America. Water is always moving, always connecting, always tying the planet together. But the water cycle is not perfectly closed. Some water is removed from the cycle for long periods. When snow falls on Antarctica or Greenland and doesn't melt, it accumulates layer upon layer, forming ice sheets that can be kilometers thick. This ice can remain frozen for hundreds of thousands of years, effectively removing water from the cycle. During ice ages, when the ice sheets expand, so much water is locked up in ice that sea levels drop by more than 100 meters. Coastlines shift. Land bridges appear between continents, and when the climate warms and the ice melts, that water returns to the ocean and sea levels rise again. Water also gets removed from the cycle through subduction. At places where tectonic plates collide, one plate is forced beneath the other, descending into the mantle. Sediments on the ocean floor, which contain water in their minerals, are carried down with the plate. Some of this water is released as the rocks heat up and partially melt, feeding volcanoes at the surface. But some of it is carried deep into the mantle, where it can remain for millions of years before eventually being recycled back to the surface through volcanic eruption. In this way, water cycles not just through the surface and atmosphere, but through the deep earth as well. It's part of a planetary system that extends from the ocean floor to the upper atmosphere and down into the mantle. Water is everywhere, in every layer of the planet, constantly moving, constantly transforming, and always it returns. That's the remarkable thing about water. It never disappears. It changes form, solid to liquid to gas and back again, but it doesn't vanish. The water that filled the first oceans is still here. Some of it is in the deep ocean. Some is frozen in glaciers. Some is in the atmosphere, drifting as vapor. Some is in the ground, flowing slowly through aquifers. Some is in living things. And some, right now, is in you. There's a concept in science called the residence time, the average amount of time a molecule of water spends in a particular reservoir. For the atmosphere, the residence time is about 9 days. That means that on average, a water molecule in the atmosphere will fall as rain or snow within 9 days. For rivers, the residence time is a few weeks. For the ocean, it's about 3,000 years. And for glaciers and ice sheets, it can be tens of thousands of years or more. But eventually, no matter where it is, water moves on. The molecule that's in your body today will be gone tomorrow. It will be exhaled, or sweated, or excreted. It will return to the environment, and it will begin the cycle again. It might evaporate and become part of a cloud. It might flow into a river. It might be absorbed by a plant, but it will keep moving, as it has for billions of years. This constant motion, this endless cycling, is what makes water so essential. It's not just a substance, it's a process. It's a connection. It ties together the living and the non-living, the past and the present, the earth and the cosmos. Without water's ability to move and transform, Earth would be a very different place. It might not be a living place at all. Consider what water does for life. It's not just that living things need water to survive, though that's true. It's that water makes life possible at a chemical level. Life is chemistry, and chemistry requires a medium. In a solid, molecules are locked in place. In a gas, they're too spread out. But in a liquid, molecules can move and interact while still remaining close together. Water is the perfect medium for this. It's liquid over a wide range of temperatures, from 0 to 100 degrees Celsius at normal pressure. It dissolves a huge variety of substances, allowing nutrients, minerals, and waste products to be transported in and out of cells. And its molecular structure, with one end slightly positive and the other slightly negative, makes it incredibly versatile in the kinds of chemical interactions it can participate in. But water does even more than that. It stabilizes temperatures. Because water has a high heat capacity, organisms that are mostly water don't heat up or cool down too quickly. This allows for more stable internal environment, which is crucial for the complex chemistry of life. Water also has a high heat of vaporization, meaning it takes a lot of energy to turn liquid water into vapor. This is why sweating cools you down. When water evaporates from your skin, it carries away heat, lowering your body temperature. And then there's the strange and wonderful fact that ice floats. Most substances are denser in their solid form than in their liquid form, but water is the opposite. When water freezes, it expands slightly and becomes less dense. This is why ice floats on water. And this seemingly minor quirk has enormous consequences. If ice sank, lakes and oceans would freeze from the bottom up. During winter, ice would accumulate on the bottom, and over time, entire bodies of water could freeze solid. Life in those waters would be impossible. But because ice floats, it forms a layer on the surface that insulates the water below, allowing life to survive beneath the ice through the winter. It's a small thing, a quirk of water's molecular structure, but it has shaped the evolution of life on Earth. So when we ask where water came from, we're not just asking about the origins of a substance. We're asking about the origins of life, of climate, of the planet's habitability. Water is not separate from Earth's story. It is Earth's story, and understanding how it got here helps us understand everything else. Now, as we near the end of this journey, let's take a moment to step back and see the whole picture. Imagine the timeline stretched out before you. At one end, 4.6 billion years ago, a cloud of gas and dust collapses, forming the solar system. Water is there from the beginning, frozen in the outer reaches, evaporated in the inner region. Earth forms, hot and dry, losing any water it might have had. But the solar system is still chaotic. Asteroids and comets, nudged by Jupiter's gravity, fall inward. They strike Earth. They deliver water, impact after impact, over hundreds of millions of years. At the same time, deep within Earth, water trapped in minerals is released by volcanic eruption. Steam rises into the atmosphere. The planet cools. The steam condenses. Rain falls. The first puddles form, then streams, then lakes, then oceans. By 4.4 billion years ago, just 200 million years after Earth formed, there is liquid water on the surface. The oceans have arrived. Life appears soon after, perhaps by 3.8 billion years ago. Simple cells living in the warm, mineral-rich waters. Over time, those cells evolve. They spread. They diversify. They change the planet, filling the atmosphere with oxygen, altering the chemistry of the ocean. And through it all, water is there. It's the medium. It's the solvent. It's the stage on which the drama unfolds. Continents rise and fall. Ice ages come and go. Mass extinctions wipe out countless species, but life rebounds. And always, the water cycle continues. Evaporation, condensation, precipitation. Water moves from ocean to sky to land and back again, tying the planet together, connecting past and present. And now, 4.6 billion years later, you're here. You're reading these words or hearing them, and somewhere in your body is a water molecule that traveled across space to get here. A molecule that survived impacts and heat, that cycled through ancient oceans and ice ages, that was part of countless other living things before it became part of you. And soon, it will move on. It will leave your body and return to the world, and the cycle will continue. There's something deeply humbling about this. We live such short lives, decades if we're lucky, but the water in our bodies is billions of years old. It has seen the entire history of the planet. It was here before us, and it will be here after us. We're just temporary custodians, borrowing it for a brief moment, and yet we have the ability to understand this, to trace water's journey back through time, to see the connections, to realize that we're not separate from the planet, but part of it. That's a kind of miracle in itself, that the universe, through billions of years of evolution, has produced beings capable of looking back and understanding their own origins. But understanding comes with responsibility. Because now we know that water, for all its abundance on Earth, is precious. It's not evenly distributed. Some parts of the world have too much, others too little. And as the climate changes, driven by human activity, the water cycle is changing too. Droughts are becoming more severe in some regions, floods more frequent in others, glaciers are melting, sea levels are rising. The patterns that have sustained civilizations for thousands of years are shifting. Water will survive. It always has. It's been through far worse. Snowball Earth, global volcanism, asteroid impacts. It endured all of that and more. But we might not be so resilient. We depend on water in very specific ways. We need it to be in the right places at the right time. We need rivers to flow predictably. We need rain to fall on our crop. We need aquifers to recharge. And when those patterns change too quickly, when the reliability we've counted on disappears, we struggle. So perhaps part of understanding where water came from is also understanding what it means for us now. It means recognizing that water is not just a resource to be used. It's a planetary system to be respected. It's a gift from the cosmos, delivered across billions of years, that has made our world what it is. And if we want to continue living on this world, we need to work with that system, not against it. This doesn't mean we need to stop using water. Life requires water. Civilization requires water. But it does mean using it wisely. It means recognizing that groundwater, pumped from ancient aquifers, is not renewable on human timescale. It means protecting watersheds and wetlands that filter and store water. It means managing rivers and lakes in ways that balance human needs with the needs of ecosystem. It means adapting to a changing climate and finding ways to live with less certainty, more variability. And it means remembering the story, remembering that every drop of water has traveled an unimaginable distance to be here, that it's cycled through the planet for billions of years, that it's been part of ancient oceans and ice ages and countless living things, that it connects us to the cosmos and to every other living thing on Earth. When you remember that, it's harder to take water for granted. It's harder to waste it or pollute it. It becomes something worth protecting. So maybe the question of where water came from is not just a scientific question. It's a philosophical one. It's about understanding our place in the universe, about recognizing that we're made of the same stuff as stars and planets and comets, that we're not separate from nature, but part of it, that the boundaries we draw between ourselves and the world are illusion. We are the world, looking at itself, trying to understand itself. And in that understanding, there's a kind of peace. Because it means you're never truly alone. You're connected to everything. To the rain falling outside your window. To the ocean on the other side of the world. To the ice caps at the poles. To the water vapor in the atmosphere. To the rivers and lakes and aquifers beneath your feet. To every living thing that depends on water. And beyond that, to the asteroids and comets still drifting in space, to the molecular clouds between the stars, to the universe itself. You are made of water, ancient cosmic water. Water that has seen the birth and death of mountains, the rise and fall of ocean, the appearance and extinction of countless species. Water that was delivered by stone and ice across the vast emptiness of space, that survived the violence of impact and the slow, patient cooling of a planet. Water that found, against all odds, a home. And now, as you sit or lie, wherever you are, that water is part of you. It's in your cells, in your blood, in your thought. It's flowing through you, as it has flowed through the planet for billions of years. You're not just drinking water. You're part of the water cycle. You're part of Earth's long, continuing story. So the next time you drink a glass of water, pause for a moment. Think about where it came from. Not just the tap or the bottle, but before that, the reservoir or river, and before that, the rain that fell, and before that, the cloud it condensed from, and before that, the ocean it evaporated from, and before that, billions of years of cycling through the planet, and before that, the asteroid or comet that delivered it, and before that, the molecular cloud where it first formed, and before that, the stars that made the oxygen. That's the journey. That's the story of water. It's a story that stretches from the beginning of the universe to this present moment, from the hearts of dying stars to the glass in your hand, from the vastness of space to the intimacy of your body. It's a story of connection, of transformation, of patience and persistent. It's a story that reminds us that nothing is truly separate, that everything is connected across time and space, that we are, all of us, part of something vast and ancient and beautiful. And perhaps, in the end, that's the real gift that water brings. Not just life, though that alone would be enough, but understanding. The understanding that we belong here, that this planet is our home. Not because we were placed here by some external force, but because we grew from it. We are made of Earth, and Earth is made of the cosmos. We are, in the most literal sense, the universe experiencing itself. So as the night deepens and your thoughts begin to slow, let that understanding wash over you like water. Let it seep in, the way rain seeps into soil. You are part of this story. You always have been. From the moment those first water molecules formed in the cold darkness between the stars, to the moment they reached Earth, to the moment they became part of you. You're not separate from any of it. You're woven into it, thread by thread, molecule by molecule, and that's something worth resting in, something worth carrying with you as you drift towards sleep. The knowledge that you're made of stardust and ancient rain, that you're connected to everything that has ever been and everything that will ever be, that the water in your body is older than mountain, older than ocean, older than life itself, and that tomorrow, when you wake, that water will still be there, still cycling, still connecting you to the rest of the world. The journey of water is not over. It will never be over. As long as Earth exists, water will continue to move and transform and connect. And as long as we exist, we will be part of that cycle. Borrowing water from the planet for a little while, then returning it. Taking our place in a story that began billions of years ago and will continue for billions more. So rest now. Let the story settle. Let it become part of your dream. And know that wherever you are, whatever you're feeling, you're never truly alone. You're part of the water cycle. You're part of Earth. You're part of the cosmos. And that connection, that belonging, is yours to keep forever. Thank you for joining me on this journey. Thank you for wondering, for listening, for letting yourself be curious about something as simple and as profound as water. If you found peace in this story, if it helped you see the world a little differently, I'd be grateful if you'd share it with someone else who might need it. And if there are other stories you'd like to hear, other mysteries you'd like to explore, leave a thought in the comment. This channel exists because of your curiosity, your question, your wonder. Until next time, from all of us at Earth's History, sleep well, dream deep, and remember, you're made of water, ancient, cosmic, irreplaceable water, and that makes you, quite literally, miraculous. Good night.